So today, Don invite Dr. Riousset from Florida University. So I hand over to the Don and introduce the speaker. Please, Don.
Hi, everyone. Thanks for joining us a little bit earlier than normal. Like Tada-san said, the speaker today is Jeremy Riousset. He is from France. He actually grew up right around the corner from my wife, in the same part of France. They are first cousins, I think. It's a big family, so I don't remember the exact relation, but professionally, he earned his undergraduate degree in France and then eventually wound up at Pennsylvania State University for his PhD. He did a couple of postdocs and currently is an assistant professor at Florida Institute of Technology in the Aerospace Physics and Space Sciences Department. I'm glad you included that, Jeremy, because I remembered there was 3 things in the department name, but I couldn't remember what the 3 things were. And today he's going to tell us about planetary lightning and the current state of the art. So please, Jeremy, take it away.
Okay, so good morning, everybody.
Morning.
I think.
Wow.
So what I'm going to do right now is focus on an overview of what we know and what we don't. And I'm going to focus mostly on what I've worked on the theoretical part of the planetary lighting. So I'm going to do a brief overview about the various planets in the solar system and the various bodies where we can expect lighting, and use that as an opportunity to discuss which processes are common and what can be different. I'm focused on a recent publication that was published in Icarus in 2020 by myself and a few colleagues here, and then introduce how we can use our current knowledge on Earth to understand processes on other planets. So let me start by a little bit of motivation. You may all be familiar, if you've followed the science news, about the discovery of phosphine in the atmosphere of Venus that cannot, to this day, be explained with an anabiotic process. So suggesting it could be a possibility that it came from bacteria. But to start bacteria, we need fundamental bricks. And those fundamental bricks, the amino acids, have been related to the presence of relatively straightforward gases like CH4NA3 inert gases, which can be recombined into amino acid in the presence of a spark. So it is believed that, at least on Earth, one of the reasons we developed life is because we had lightning as a source of power to transition from inert gases to amino acids. If this process happened on Earth, it could happen somewhere else. And that somewhere else is where I want to go next. I'm going to use a publication in EOS recently by Cartier, and that distinguishes between the haves and have-nots, and I'm going to modify a few things. On this plot, I show which bodies in the solar system have recorded a lighting activity. Well, naturally, Earth, okay, it's even how we define it, as a very energetic, focused discharge process. But here, rather than showing you a thundercloud, I showed 2 specific elements. So let me see if I can point. Yes, I should be able to point. There we go. So in that case, the upper case is a sandstorm in Arizona. So, and what we see here is actually lightning developing in a sandstorm. No water needed, just collisional with sand. Another one is actually probably more familiar to some of you because it's actually a Japanese picture, the volcano in Japan, that demonstrates that volcanoes are when they are erupting, are creating conditions satisfactory to propagate lightning. So that's for Earth. In addition to thunderstorm, sandstorm, and volcano, they all can produce lightning. A couple of moving to other planets. This this middle panel that I'm highlighting here is a recent publication on Jupiter, what's called the mushball clouds. These mushball clouds are also expected to have lightning discharges, but lightning has been discovered on Jupiter way before by Juno spacecraft and by the Galileo spacecraft. So basically, we've seen storm on Jupiter, and ever since we've seen storm, we also have seen lightnings. Okay. The third case is Saturn. Saturn, with this one is a Cassini mission, has shown us that we can have lightning activity in those cloud structures. And actually, if you were to zoom in, you could see at this location we have lightning. A better way to do it is hopefully play that, and we can see a zoom in on one of those storms. I do not know if the sound plays, but every single of these flashes is a lightning. Okay. The way we've detected those is optical and through radio frequencies, so we can also detect them remotely. Moving a little further now, we can look at planet Uranus, and on the planet, we observe very bright storms indicating lightning system. Some of these storms have a size comparable to Earth. If you look at those and the rebrightening. So through radio observation, through optical observation, we've been able to try to assess and confirm these planets have lightning activity. Next, we go to the possibles. The reason I chose the cases of Earth is because I showed you some volcanoes, and we know a couple of things. Those are obvious artist rendering on Venus that were created during the Venus Express mission. And what they show is that Venus has volcanoes, or at least may still have active volcanoes. Those could be a source of lightning. A second opportunity, and that's what I'm looking at in the upper part, is higher level cloud. So in the cloud deck, and I'm going to get back to that, which also could create conditions for lightning. So here we're looking at optical images. Unfortunately, nothing has been detected so far, and it's quite difficult to understand. On the right-hand side, using the same method as we did for Saturn, we can observe whistlers. Whistlers is this actually band. In this ionogram, we can see a band which is that we can convert to radio signal, a radio signal that is typical for lightning propagating in an ionosphere. So using this radio signature, we think that Neptune also has lightning, but it's not been confirmed. The why nots are the planets or the bodies that have everything to create lightning, but no conclusive observation. So on the left-hand side, Mars. Mars has dust events that are similar in terms of electrification to Earth sandstorms. So fundamentally, nothing is telling us that there should not be lightning on Mars. We even had a case in the publication by Riousset in 2009 that we have an emission, a radio emission that could not be explained and still isn't really explained, that was associated with lightning. However, our inability to ever reproduce or observe any signature like this kind of raises concern about what is that? Is that really lightning? And I'll go into why I think we may be looking at the wrong thing. On the right-hand side, we look at a volcano on Io. And again, this is a situation where, well, we have a volcano with a gigantic plume, which means that we could potentially create condition for lightning. And So from this, I'm going to try to summarize a couple of things. What do we need for lighting? What we need is an electrification process, meaning the presence of particles that can be collided to create charge separation. We then need a mechanism to separate those charges. So it's a mix of either an updraft, take a wind along the side of a mountain, then this wind will lift up particles. That's exactly what happened in winter thunderstorm in Japan, for example. Moist wind get raised against the mountains in the central part of Japan, and that bring us water molecules that are easily electrified. Then gravity will separate the particle with positive and negative charge by weight, and between those regions where we have positive and negative charges, we form an electric field. When the electric field is high enough, we trigger lightning. So that's what for normal storm on Earth. If we go to a sandstorm, same process. We lift up dust. We have collisions between the dust, and from that we create 2 layers of charge, an electric field, and we produce lightning. So for Mars, what we'll look at is what could happen now. So that's a visualization I had a student creating of Mars with exaggerated relief. It's dry, but it has a lot of sand that then creates sandstorms. But 4 billion years ago, Mars could have looked like that with a lot of water. And in that case, there could have been also a reason for lightning activity on Mars. So the type of lightning we'll explore here are categorized between lightning, regular, that we see in the storm or below, and upper discharges. They can be blue jet, gigantic jets, and sprites, which are very different. Upper atmospheric between maybe 30 and 100 kilometer high. Those are quite different because here we have very hot thermalized channel. Here we have much less ionized channel, much cooler temperature. And I think there may be a reason why we could easily detect those with a strong signature, but these might be harder to detect. And on planets like Mars, I don't think we would have detected them by now. So a lightning is what? Lightning is fundamentally an electron avalanche. If we have an atom and a very highly charged, a very fast electron, then the collision will liberate an electron from this neutral, and the original electron can continue to ionize another element, and the newly freed electron will ionize another particle. That is reproduced in what's called a cascade, creating the channel. Depending on the intensity of this discharge, of this cascade, we can create what's called streamer discharge, leader discharge, or coronas. And this just means that you have different channel, different ionization with different properties. But to understand better how lightning is created, we need to understand the environment in which it's created. To do that, what we do is use atmospheric models, which will give us a fraction of the various species in the atmosphere and the temperature, to calculate what is the electric field that will initiate, that will separate effectively the electron from the nucleus in order to start this avalanche I just talked about. So that part of the work I've done and we published is, well, for Earth, we have a few good data. It's easy to have profiles, fraction of each particles, and then with the temperature, create what electric field as a function of the altitude is necessary to create lightning. When I did that, I said, well, if I can do it for Earth, I should be able to reproduce it for other planets. I do it on, for example, on Venus. And you see on Venus, if we were just to look at the numbers, what's interesting here is that you have the altitude versus the strength of the electric field, that at low altitude, the electric field necessary is much higher than it is on Earth. But when you reach the cloud layer at 50 kilometers, then we will actually have similar condition that we have on Earth. Reproduce it again, but now for Mars. For Mars, we can see that it's actually quite easy, just looking at the numbers of the electric field, to initiate a discharge in the lower region. Obviously, when I present those, it's a bit overwhelming. So what I did is, you know what, let's just collapse them into a single slide. In that slide, on the left-hand side, we see the electric field for the 3 planets. Red is Mars, blue is Earth, and black is Venus. We can see that for Venus, the amount of strength of the electric field that is needed is significantly higher than for Earth and for Mars. The evolution we see is mostly driven by the pressure. So a low pressure means a lower electric field to initiate a discharge, which is the reason why we have discharges in the upper part of the atmosphere at 100 kilometers. But if we remove the pressure factor, we should be able to tell that actually Mars and Venus should line up because they are essentially CO2. And that's what we see on the right-hand side. If I remove the pressure dependence, well, then I have Mars and Venus very similar in terms of condition for initiation. So this gives us an idea that on Mars and on Earth, it's likely that discharge, if they occur, are in the lower atmosphere, while on Venus, if they occur, it's in the higher atmosphere, and actually where phosphine has been detected. So moving on is what we'll have is how do we test our hypothesis? On Earth, when you create a charge separation, the lighter charges are positive and they're raised by the updraft in the upper part of a cloud. So for example, that is about, I would say, 12 kilometers, and that is about 5 kilometers. Okay, the lowest charge region is still positive charges, but I will put it aside for now. When I do that, I can compare these lines, the green lines that you see here, were essentially the same grid lines that were this blue line here. Okay, I just positive and negative. I calculate the electric field created by something like this and look at where the discharge, where the field is too high to be sustained by the cloud. So that occurs here around 8 kilometers. When I move that to, when I try to simulate that, what do I get? Well, I need to introduce these branches. I need to introduce the fact that lightning is stochastic. To do that, I use what's called a fractal approach. The fractal approach is just saying, look at where the lightning is and look at where it stops and look at what the possible option it has to propagate. So we just look at the electric field at the end of each branches, and if it's higher than a certain value, then it becomes a possible propagation. I list all the places lightning could propagate, and then I randomly select one, and I iterate. When I do that in 3D, I obtain a classic intra-cloud discharge showing what lightning would be is on Earth typically. 2 levels between 5 and 10 kilometers. That is most lightning on Earth. Let's say probably between 60 and 80% of them. But if I've moved to Mars, there is a lot of unknowns. How big are those clouds? Where are the charges? What are the thresholds? But we can use at least a small schematic and say, okay, well, if I look at what I expect a dust devil to be, it's going to be about 10, 20, maybe 20 kilometers wide in the upper part and maybe a few kilometers, 5 to 10 kilometers narrower on the bottom part. I see that my positive charge are mostly on the bottom and I have some negative charge on the top. I have an updraft lifting up the negative charges, which are basically dust storm. If I do that, I can just say, well, as a first approximation, I'm going to create 2 layers and charge them with equal and opposite charges to maintain neutrality and look where the field is high. If I do that, that's exactly what I did. I can look and say, okay, well, in that condition, I should expect lightning to be initiated around 6 kilometers. So I do that. I put my 2 charges, I put my cylinder, I initiate my discharge, and when I propagate, it will look like that, just for a few distance. So that in the fractal approach, that's what it would look like on Mars. That's something that I'm trying to finalize. But that is probably one, if not the first, three-dimensional simulation of Martian lightning if it exists. To wrap this up, I just want to emphasize on a couple of things. The first one is lightnings might be everywhere, but whether we are looking at an actual lightning similar to Earth, very hot, very ionized, or a streamer which is not as hot, not as ionized, is unknown in many cases, and that affects our ability to detect it. It also affects the value for propagating the lightning in the fractal model. So we also don't know much about the electrification processes. Those create hindrance. However, with observation, it's relatively easy to adapt Earth models to extraterrestrial lightning. And that's exactly what I was trying to show in something like that. I think that's probably a little bit on 15. Yeah, that's almost 20 minutes. I'm sorry. But if you have any question, I'm happy to answer.
Okay. Thanks, Jeremy. Yep, we're all applauding, but we're all muted, so you can hear it.
Thank you.
While we wait for people to ask questions, either in the chat. Oh, Kodama-san, you have raised. No, you're applauding.
No.
Yes.
So Uranus has lightning, Jeremy, and Neptune apparently doesn't. But these are fairly similar planets in terms of composition, right?
Yes,
In
but
size.
okay, that's a very good point. So a couple of things. What is the biggest difference between the two?
Distance from the sun.
Exactly, which means how much sunlight they will receive. And since sun is the engine of anything happening in the solar system, what it will affect is the insolation, the amount of energy it receives, how how the clouds are heated. That's major. And in addition, the amount of water in the atmosphere, the fact it will be more likely to be ice, will probably affect the albedo, and therefore how the thermal influx can be converted into an effective updraft process. It is perhaps, as you said, if you look, Neptune, we're sure we've seen them, optical, all good. Neptune, we have signals that suggest, yes, it should be there, but it's still unconfirmed.
Okay. Does anybody else have questions?
Hatsuda-san is raising his hand.
I'm sorry, I am looking at the wrong screen. So I guess Hatsuda, please go.
Can I? Okay. So in your stochastic model, you have some initial point of the ionization. How do you choose that one? It is randomly chosen, or?
So that's an option we have. So let me go back at least. Yeah. So for example, if I look, the Earth is easier to see, but for the Earth, when you have a charge structure like that, we have a three-dimensional model that allows us to calculate the electric field everywhere. So what I'll look is every point in the simulation domain that exceed this value right here can be a starter. And then I'll pick randomly. I'll set that as a probability and pick a random number that can be either equiprobable, that can be depending on how strong the lightning is above the threshold to start the lightning.
Okay, and then after this ionization, the positive charge moving up and negative one moving down, right?
Actually, it's interesting because it's the opposite. Since the goal of lightning is to reduce the field,
yes,
the positive lightning goes into the negative layer, and the negative light part of the lightning go into the positive layer. So if you look at something like this upper part here will develop into the upper positive charge region, which means it's negative. And this one propagates in the central negative charge region. And that's why this part is positive. And the effect of this is a reduction of the electric field. It's a sample right now through the axis, but basically the goal of the lightning is to reduce the electric field stress.
But then I'm confused because you said that the initial, the separation of the electric charges, the gravity act, and then the light one goes up and then heavy one goes down. That means that the electron goes up and then other nucleus goes down.
It's a very valid point. However, I may have spoken too fast here. What happened to this electron when it's separated? It reattached to another particle, to another bigger element. So, for example, on Earth, the bigger elements are called groupel, and the groupel are basically small hail. It's hail. Sorry, I struggle with that word, which are heavier than the particles that carries the negative charges. The positive charges are carried by the supercooled water droplets, so by very tiny particles. So they are lifted up more easily and they carry with them the positive charge, while the negative charges is carried by the groupel, which is heavier, and that goes down. And that forms the central region. The reason for the lower positive, the reason for this third layer is because there is also temperature inversion at which charge carries which layer, which polarity changes, but it's a different story.
Okay, thank you.
So I just went to the English Wikipedia page, found groupel, which is a word I did not know, and looked at the Japanese equivalent. So I don't know if this is a technical term or if it's something everyone else in the common room has seen before. I posted a link in the chat.
Okay, so groupel is basically an ice ball, no more, no less. It's an ice cube.
Okay.
It's you be better than me at pronouncing HAIL. How do you pronounce that, Don?
That would be hail.
Okay, well, that's what it is. But in the case of a cloud, it's called a groupel.
Well, Hasuda-san has lowered his hand. I guess he no longer has a question.
So can I ask a question?
Please do.
Okay, thank you very much for very enlightening talk. So you actually briefly mentioned that, if I'm not mistaken, that making a charges process is not really clear, but is that right? So what do we know why those clouds are charged or those charges separate? So
then our understanding of even Earth's cloud is incomplete, but our knowledge is based on experience, so observation. We notice that certain particle, we are able, for example, to say if you the size of a particle in a certain part of the cloud using radar data. So if you look at weather radars, when you see all these colors, the reflectivity tells us how much of the signal is sent back, and that tells us what size of particles are here. When we overlap that with maps of lightning, we can tell where the charges are, and we can do correlation that tells us, okay, that's how it happens. But most of our knowledge, especially for more difficult events, more rare events like the sandstorms that are not always electrified, for that we have lab experiments in which we will use, for example, like magnetic levitation to collide silicates, for example, and observe the formation of an electric field resulting from the collision between these dust particles and their gravitational separation.
I see. Okay, thank you. Yeah, that lightning is very fascinating things, but I can't just really explain in the teaching the electromagnetic course, that because we don't understand why it's happening. But so still we don't really have from first principle understanding of the process.
Well, Jeremy, that was your doctoral dissertation, wasn't it? Was trying to understand how lightning happens.
So I don't have it here, but I have, as part of my doctoral dissertation, a big factor was to understand the behavior of a lightning once it's initiated. Is it going to go to the ground? Is it going to stay in the cloud? Is it going to go upward? So basically,
Right.
if you look at this, what is it? This image, when will a lightning develop like this, or like that,
Mhm.
or like that? So that was part of the effort. And it is fundamentally explained by the charge configuration of the cloud at the moment of initiation. Where are the charges? How much are there? What happened to the cloud before?
Okay, great. Thank you.
Sure.
Do we have any other questions for Jeremy? I don't hear a lot of talking, so if you had questions, you left yourself muted. So if there are no further questions, thank you again, Jeremy, for staying up so late to join us here in the afternoon in Japan. I hope someday we can do this in person.
Happily.
Should
I owe you a
conditions allow.
visit. We
Yep.
owe you a visit, so.
Looking forward to it. Tada-san, Nagataki-san has a presentation to follow Jeremy. So do you want to take over sharing
Yes,
once Jeremy
let me.
signs off? Or I guess if you want to listen to a presentation, you can hang out and mute yourself.
You will have to excuse me, but I have a meeting tomorrow morning, so I'm gonna go to bed
Well,
now.
have a great night.
Thank you very
If
much.
you don't mind
Bye.
sharing
Night.
my email, you can send me questions, and if you have a space where you want to host a presentation, I could send you the slide. They are like 50 megs, I think. So, okay.
You can send a link to me and I will pass it along.
Okay.
Okay.
Have a good night, guys.
Bye.
Oh, good day. Good afternoon.
Thank you.
Okay.
Bye.
Thank you very much, Jeremy. And also thank you very much, Don, for arranging this wonderful talk. Thank you very much.